with Markus Lintl, Orcan Energy, clean electricity from waste heat. Act now and remain flexible. So wonderful. I see your screen. I see you. And then, yeah, over to you, Markus.
Yeah, great. Thank you. So first of all, thank you for having us here in this webinar where we can introduce Orcan and our clean electricity from waste heat approach. Before starting and telling you how much heat is out there, which we heard already, a few words about myself. So Markus Lintl, background mechanical engineer. However, I only worked in sales and business development since more than 10 years. And I was there when the company still was just 5 people small. So I've seen quite some things and a lot of waste heat everywhere. And luckily, we also made it already to use some of them, and that's what I'm going to present here. First of all, yeah, waste heat in the industrial processes is massive. So we're talking here about several 100 million tons of CO2, which can be still saved. And the good thing is saved with a payback. So you save costs and you save CO2. There is a business case for it. When we just look, for example, on the cement industry, we could produce as much heat as 40 million European citizens, or enough electricity as much as 40 million European citizens would consume. So it's a significant number, and cement is by far not the biggest, I would say, waste heat industry. Our customers are typically doing exactly this, or our solutions, because of the 3 reasons made here. First, save cost. I would say second and third also save cost. So it's still most important to reduce the energy bill, especially in electricity price ranges or situations and times where electricity prices are not just high, but also super unpredictable. There it helps if you can produce a portion of your electricity by yourself. Of course, since we save electricity, we also lower the scope 2 CO2 emissions, which becomes more and more relevant for our customers. And at the end, yeah, we increase the efficiency of the overall plant since it uses less electricity, which is, for example, relevant for ISO 50001 and others. I would say these are still smaller drivers. The key driver is saving money. About Orcan, I see already the slide is outdated. We are now about 100 people. We were founded 2008. We have more than 7 million operating hours on our fleet. We have more than 2 million tons of CO2 savings contracted, 600 modules out there. So I would say it's working. We've shown it out of university through several commercialization tracks that it's possible to set up a company that does nothing else but use heat and produce electricity. And yeah, we consider us as a scale up, so we're still growing. We have partners, investors like E.ON, Air Liquide, you might know. We're working in marine with Alfa Laval, have done, for example, recently a project on a Maersk ship, and have other financing investors. Yeah, waste heat is not just a Bavarian phenomenon. We are located in Munich. It's all over the world, everywhere you can find waste heat. In several industries, oil and gas. We have a project at Chevron, for example, in the US, more than 30 machines, I think, up and running in the US. On ships, you find it in cement across the world. You find it in glass industry, steel, on power plants, especially in emerging countries. So it's, yeah, that's incredible how much heat we have. And we use them, or we start using them now. Coming a bit to the technology. So you as a industrial player might be, for example, from cement or glass or steel. You have waste heat in different forms, sometimes not, but a lot of I would say energy intensive industries have waste heat. Most of the time we find somehow gaseous exhaust gas or gaseous heat. There we implement a heat exchanger, a boiler. We make hot water or for high temperature also thermal oil. This loop transports then the heat to our machines, our modules, our containers, where we produce electricity out of the heat. If there is already liquid heat available from a cooling circuit, for example, or even steam, as we have done at Glencore, at Zinkhutte, yeah, we use it directly in our machines, of course. But for accessibility, it's good to deconnect or decentralize the heat exchanger and the machines, so you're more flexible than also on site. Yeah, and then we produce electricity. The technology basic is organic Rankine cycle. Can talk later about this, but in order to make it a bit more visible, here is our most sold machine so far. So it's a 40-feet container with the complete power plant inside the machine in this container. So we have in the middle the core process with the evaporator, turbine, power electronics, and here's some coolers, cooling tower basically, and on top the water goes in and below the electricity goes out. These machines are completely produced in our factory in northern Germany. It's completely factory tested, so pre-filled and tested. It's shipped to the customer, so we have a very high quality aspect on that since we are not building it customized on site. And it's very light, very compact, easy to transport, also easy to relocate. That's also flexible. So if maybe you don't have the heat in the future anymore, just take it away and place it somewhere else. For the operation, what we hear a lot from the customers is that it's great that it has no consumables. We don't need water or oil or whatever. It completely operates autonomously. We have here one of our first companies was a Bavarian automotive company. They have only heat in the summer available. In winter, they use it for heating. And it was always funny. They always called us when spring came up, the heat demand for heating went down and said, "Hey, the machine turned on just again." We said, "Yeah, exactly, because there is a stupid temperature sensor. And as soon as it skips the temperature, we just turn on." Completely autonomously, and then we produce electricity. So we really completely autonomously follow the heat. Of course, you can always deny us the permission to operate, but in general, we follow the heat and use it. We have only 1 day per year maintenance, which is nothing for a power plant. We offer, of course, maintenance contracts, including all spare parts. One further technological insight is we only use standard off-the-shelf components. So everything inside our machine, the coolers, obviously, the fans here, but also the expansion machine, pumps, heat exchangers. It already exists for chilling machines, for heat transfer stations, for whatever. And we use them. And by this, we rely on a big supply chain, on a big market, on a big production capabilities, and spare part availability also. And we have all the know-how to operate them as an ORC and not in their original specification or original application, but still within their specification. This makes it very robust, reliable, 99+% availability, of course. And at the end, also economical viable. I will also show later a business case. Coming a bit to real customer examples. Most of the industry references we have in the most complicated industry from a waste heat perspective in the cement industry. So there it's dusty, rough and tough environment. At weTHINK, which was our first bigger cement project, we have done a clay factory before, where we also were awarded. But weTHINK is a normal cement factory here in Germany, western part of Germany, and we have a project on the clinker cooler. So until we installed it, there was a clinker cooler, high dust air. So it's ambient air heated up to 300-400 degrees, and by this it cools down the clinker, and this is full of dust, a highly abrasive dust, and it needs to be filtered. In most of or in a lot of those factories or cement plants, you have back filters, and they only can stand a certain temperature. That's the reason why the air, until now, or until a few years ago, it was cooled down actively with air-to-air coolers. So they invested electricity to get rid of the heat. Amazing. And then they filtered it and went through the chimney. And what we've done now, we just implemented in parallel an air-to-water cooler. which heats up water, and with this water we produce some electricity. So we have double savings. On the one hand side, you have no electricity consumption on your existing air-to-air cooler, and we produce electricity. In this case, about 8 gigawatt hours. Installed capacity 1.1 megawatt. Electric, by the way, all electric numbers you will hear from me are always net electric numbers. So all internal consumers like fans, pumps, power electronics, everything is subtracted. So that's the real number you can calculate with in an average year for your location. Yeah, that's what we do. And in order to leave now all the theoretics, I have some beautiful pictures in here that you can also see the size of our machines. So as a comparison here, a car, these are our 6 units. So 1, 2, 3, 4, 5, 6. They are fed with hot water from the top. And here on the other side, here behind, there is the heat exchanger. So it's, as you can imagine, and you know from your sites, there is no space for nothing available. So you really need to find flexibly some locations. And so containers, which you can easily put here, there, wherever, you typically find easier available footprint. In this case, it's actually exception that we have so much at once. A lot of times we have 2 here, 2 here, 2 there. So we can also decentralized place our machines. About the scope, we started as an ORC company, building only the containers, and we hoped that somebody would just buy thousands of them and install them, and we are a happy big company. At the end of the day, this was not the case, since the customer said, great that you make a container which produces electricity, but I also need a heat exchanger. I also need piping, steerwork, electric interface, and I want this from you. So we developed ourselves or developed an own department for EPC works, where we do turnkey solutions. In this case, we made everything from the heat exchanger, including the steel structures, flaps, water loops, electric interface, and an end. Of course, with suppliers, renowned suppliers from the industries, and installed it. So this is the heat exchanger. It's quite big. We needed heavy-duty transport and anything, which is in the dust. So you have here the exhaust gas flowing within the pipes. There are 1,000 something pipes or tubes, and it's surrounded by water. The water is heated up, and this heat goes then to our machines, and we produce electricity out of it. So rather simple. In this case, we have a 2-stage heat exchanger so that we can cool down the heat maximum possible. So we also have a low temperature loop here with 80, 90 degrees where we preheat our fluids. This is just weTHINK. Few more facts: 2 years of operation, no problems with dust, TÜV, and everything is there always to monitor it, but it's a robust, proven technology. We are quite quick with these containers, as you can imagine. So at Düsseldorf, we had, I think, 6 months delivery time from signature to first electricity. weTHINK was a bit longer. We needed to wait for a standstill to tie in, and as you can imagine, the heat exchanger had a quite nice lead time. So I would say something between 6 to 12 months is possible. That's another perspective on weTHINK, but more important here are the other references. So at Cemex in Rüdersdorf, Germany, we have a plant in operation. With Buzzi, we secured already 2 deals, one in operation in Germany at Düsseldorf, one in Italy. Then Schwenk, we are currently installing in a site in southern Germany. The press release will follow these days. With Titan, we are discussing and also published this already, a more strategic partnership for several sites, and all this just in a few years. So we see there is something happening. We also see this in other industries. Before coming to this, a few more impressions. So Cemex, I cannot see it completely here, but also here we have a machine park. That's some structures here to cross the street. In here is the heat exchanger, and are also on the clinker cooler. We have the Düsseldorf pictures. You can also see this in the press releases. In order to save a bit time, I move forward to other industries. So metal industry, zinc production. Here we use excess steam, for example. In a steel factory, there's a lot of exhaust gas and reheating furnaces and cooling circuits. And the good thing is about these industries, they're quite old. And a lot of those industries have more than one heat source, more than one plant. And of course, as you can imagine, buying more of these units, it's not getting more expensive, it gets cheaper. It's a volume effect. What we're currently doing is a lot with the bigger players in the industries. They're doing some volume contracts, frame contracts, partnership approaches, however you want to call it, since it's simply cheaper to equip several sites at once. And our technology is suitable. The same machine is suitable for all the plants. And the containers are suitable for even different industries. So the container you see here, you have seen it in cement, you see it now in zinc, you see it here in metal, recycling, lead recycling. You will see it in oil and gas. So it's always the same container. And that's something which makes it highly attractive for them, because they can then shift it from one plant to the other one when heat loads changes and. That's another application at EcoBat. Here we substituted a cooling circuit. So they have excess steam, which they condensed with the normal cooling tower, water-based cooling tower. And they only had visible 20-30 degrees warm water because, of course, this cooling circuit operated at low temperatures. Then we say, yeah, but the initial process has 110 degrees or 95 degrees in water. So we basically upgraded the cooling circuit, and now we are producing electricity instead of spending water and electricity to cool. So even heat sources, which at the beginning don't look very suitable for us on the temperature level, can be upgraded, since a lot of processes before have a higher temperature. A few more impressions. That's the one at Chevron. It's a geothermal application. Compared to wind and PV, if you look on the produced electricity, we have a quite low footprint, since we are operating 24/7. It's baseload electricity. And about the economics, I think that's, as I said, most important. Our customers, they love to save CO2, of course. They love to tell this also to everybody. But what they love even more is earning money and saving money, which I completely understand, and which is possible with our overseas. So if we look on the levelized cost of electricity for our machines, if you're only on our machines, you're 34 euros per megawatt hour. Of course, turnkey scope has to be considered. So you need some piping, you need a heat exchanger, you need some steel structure, and then you're somewhere between 50, 60, 70, 80 euros per megawatt hour. And this is, in most cases, below the electricity price of the customers. And what's very important, once the customer buys it, this electricity price is fixed over the next 15 years, 10 years, 20 years, however they calculate. We even offer fully financed solutions as PPAs. Of course, this number is then slightly higher, since a third party, a financing partner, also wants to earn some money. But in general, we see that we are in a lot of countries, even outside of high-priced Germany, already competitive. Now, making it a payback scenario, we have here one of the projects which had a very high capex, so it's really not the best we could show. We have projects with 2 years payback, but in this case, 5-6 million investment, 8 gigawatt hours production. There was subsidy actually up to 50% available. We just calculated here with 30%. That's the average you can get across Europe. So the base case was about 4 years payback. If the customer calculated, yeah, but maybe I have a slightly higher electricity price in the future, or even a lower one. So you got some sensitivities, and here you can see 30-40 euros per megawatt hour more is then related to 1 year payback less. We have customers that still decided 3-4 years ago, they calculated with 70-80 euros per megawatt hour, a payback of, I don't know, 3-4-5 years, depending on the funding. And now they have 120 euros per megawatt hour, so payback was quite good. So there is some uncertainty, but also some chance in the electricity price. There is funding available. That's why we also asked the question before. Up to 60% sometimes even. It's also interesting to see OPEX is not really having a heavy impact on the payback, since it's rather low, as mentioned before. And then also operating hours has not such a big impact. I mean, we can deal with that. So if there is less heat, we turn off 1, 2 machines. If there is more heat, we can add machines, which we also are currently doing. That's a good overview. To the next one, ORC is not new. So it's really, really not new. Just a second. It's not new. So there is waste heat recovery on module, I would say use case optimized power plants, both on ORC and steam cycles available. What we have done is this flexibility and modularity, so we can adapt to changing heat situations. So if you would install a steam turbine or a big ORC turbine, you're fixed on a design point. And once your heat changes, well, you still have the CapEx deployed, and the efficiency typically goes down as soon as you leave the design point. With our modules, if there is less heat available in the future, we just take them back. So you get money back, and then the payback maintains stable. Even if there is more heat available, as I said, we add more modules. So the economics are, in the most cases, we have seen as soon as flexibility is required, and you hardly find customers who can tell you how their heat situation is in 10 years. And carbon capture, potential heat users on heating grids, any, for example, drying processes which might come up have all an impact on the heat source. And yeah, that's a bit the advantage of this modularity and flexibility. Here's one example from another cement player where we are part of a big heat user system. I want to brought in this slide because, I mean, at the end, let's face it, we have horrible efficiency as ORC. So we get 100% heat, we produce something between 10–20% electricity, depending a bit on the temperature level. So if you can use heat as heat, please do that. That's 100% efficiency, so go. Most of the heat-to-heat users are already done because there was always a good business case. The problem is that the heat user is a lot of times not synchronized with the heat producer. Actually, for example, district heating, on smaller heating grids, you only have 2–3,000 hours of operation, and that's then with which you have to pay back as I said, quite complex and big installation. And we are a lot of times part of a heat user system, weTHINK, for example, or Cemex, where there is a drying process prior to us, so it takes a bit of heat away. At BASF, it's the same. Then there is a drying process after us. There is a district heating grid in competition of us for part of the heat, sometimes full of the heat. And we are lowest priority. So as soon there is a few thousand hours or a few megawatts available, we produce some electricity. And by this, we are a lot of times just enabling a business case. Because just for 2,000 hours district heating, it's difficult to pay back all the equipment. But with additional electricity, which you always can need, and you always can process within your factory, there becomes a business case. So the approach is a bit, let's make the most out of the available heat, and you always can start with us. There is a payback, and then add maybe heat users or do it directly in parallel. That's it. So if you have heat, let us know, and we can make an evaluation and hopefully a competitive offer on that.